So Module 8, we're getting towards the end. So in Module 8, we're going to be talking about torque and rotation. And so this is another big area where we can see things in our everyday lives. And I feel like this is next to forces, this is one of the most applicable topics to things that we see happening every day. So a torque, what is a torque? Well, a torque is it's an action that causes something to rotate. Basically, a torque causes a rotation. So if something's rotating, there's a torque acting on that object. And so the parallel is a torque to rotation is pretty similar to a force to translation. Or if you apply a force to a box, it's going to move along the ground. So if I have an F here, it's going to go this way and end up like that. So forces cause an object to translate. Torque causes an object to rotate. And so again, I'm going to highlight, if looking around you, the next time you're out and about, or even just at home, take a look around. See things rotating. Look around, see what rotates. There's a torque acting on that object to make it rotate. And so take a second to think about that and figure out what is that torque? What's applying that torque? What's causing that torque that's making that object rotate? So up here at the top left, I have the sustainable energy, a wind turbine. So the wind's applying a force on the turbine's blades. That's causing the whole blade shaft. See, these are all connected. So that's causing the whole blade shaft to rotate. And that rotation is what's turning a generator. And that's how we are generating that power. So we're using the wind to apply a force which causes a torque to act on this blade, which then produces energy. You can miniaturize this into something that you probably have in your house, which is just a common blade fan. And so there, it's the opposite. So you have a motor that's applying a torque on the blade shaft, and that's what's causing that whole blade shaft to rotate around. For people that are going into architecture, sure, I have no idea how to spell that. Architecture, or like civil engineering or construction. Torques are happening at any kind of joint in a building. So you want to be cognizant of how you design your structures, what materials you use, because torques are bad for materials. That's when a building fails or a bridge fails. Usually it's because of a torque that somebody did not account for that's causing the material to rotate. And so it's causing the material to rotate in a way that it's not designed to rotate. And so what happens is that material fails. So that's where like shear occurs, where the material kind of rips away from itself. And that's where that failure occurs, and that's what happens in bridges and buildings and stuff of that nature. Then we come to a really big part, and that's the human body, our muscles. So any kind of athletic training or, a physical therapy, stuff like that, sports medicine. So the biomechanics is the subsection of this field of how physics relates to the human body. So if you're moving your arm, you're rotating about your elbow. So say I'm bringing my forearm up this way. You're rotating this forearm about this elbow point. So whenever we're dealing with rotation, we're always going to be talking about rotation about a point. And so there's always going to be some sort of axis that we're going to be talking about. Where is something rotating about? There always has to be some sort of, you can think of it as a coordinate system, much like we did with forces, where something's acting about that rotation point. So for here, we've got the bicep here, and that's applying a force upwards. That's what's causing our forearm to rotate upwards. And so we're having a torque that's causing a rotation this way about the elbow pivot point. So looking at our equation over here, torque is equal to the distance from the pivot point, distance from pivot. F is the force that's acting at that distance from the pivot point. And theta is the angle between the vectors. Much like where we had work is equal to F d cosine theta, where that theta is the angle between those two vectors, the same thing applies here, where that theta is the angle between the F and the R vector. And so we have a force, the force of the bicep here. I'm going to get rid of these. We've got the force of the bicep here. We have a distance R from the pivot point, the elbow joint. So that's R, we'll say the bicep. And so the torque will just be equal to, and this is a 90-degree angle, the torque is equal to F bicep times the distance to the bicep from the elbow joint times the sine of 90 degrees. And so that's equal to 1. And so you're just left with this torque. In the problems that we're going to be looking at in this module, we're only going to be dealing with rotational equilibrium. What does that mean? Well, if we're in equilibrium, what does that mean? That means that we're not moving. So in rotational equilibrium, that means we're not rotating. So we're always going to have the sum of the torques equal to 0. So we're not necessarily going to be dealing with a case like this that we just did. There's always going to be another torque acting to balance out. Much like with forces, where we have a positive force and a negative force, the weight force and the normal force for an object that's stationary, those are equal and opposite. Same sort of thing is going to be happening here. For the object to not be rotating, we need to have a positive torque and a negative torque acting. Here are the learning objectives for Module 8. We're going to be calculating torques, kind of like we just did on the previous slide. Given axis of rotation, what does that mean? Well, that means the pivot point. So where is object rotating about? Draw a rigid free body diagram. So here's that word again, free body diagram. This pops up. So basically what that means is we're just going to be including the whole object. So instead of, so for an FBD, we have just a point for, say, a piece of wood and forces acting on it. The free body diagram, we would just represent that as a dot. For a rigid FBD, we will have the full picture with the forces, and then we need to choose a pivot point and deal with the torques as well. So that's a force, and then we need to deal with torque 1 and then torque 2. And so that's the difference between a free body diagram and a rigid free body diagram. Axis of rotation, just talked about that. And then equilibrium spots, where we're talking about it's not rotating and it's not translating, kind of what we just talked about in the previous slide.